Good day. This is our third video in calculations related to Ka and Kb. And so first of all, this is just showing you that Kw equals Ka times Kb. And what that means is the K for an acid and the Kb for its conjugate base. So here H2S is the weak acid, and there's its Ka expression. And the conjugate base of H2S is HS minus, and here's its Kb expression. Well, when we multiply these out, the HS minus here is canceled by HS minus there, and the H2S is canceled by H2S. What's left behind is Kw equals H3O plus times OH minus, stuff we know to be true. This is the most likely way you're going to use this formula. You have a chart of Ka values for many weak acids. So often you'll be asked to find the Kb for a conjugate base of a particular acid. So get used to using this formula. In the rare event that I gave you a Kb and asked for a Ka, then it'd be Kw divided by Kb. So we're going to start off by doing some examples of these kind of calculations, and then we'll deal with a weak base and figure out a pH and things like that. So we have a bunch of weak acids, and we're interested in the Kb's for them, for their conjugate bases. So if we have acetic acid, we get rid of the H and it's CH3COO minus, which is the acetate ion. Get rid of the H and we're left with F minus. Get rid of the H, we're left with Cn minus. Well, we look up on our chart and we see the Ka is 1.8 times 10 to the minus 4. Oh, sorry, 1.8 times 10 to the minus 5. And we go Kb equals Kw divided by the Ka, this number here. And we get 5.6 times 10 to the minus 10. We do the same thing for HF. The only difference is we put in this Ka, 3.5 times 10 to the minus 4 based on the HF. And we get 2.9 times 10 to the minus 11. That is the Kb for F minus. And the same thing for HCN. There's its Ka. It goes here. And we get 2.0 times 10 to the minus 5 is the Kb for Cn minus. Hopefully that's clear. So the larger the Ka, the smaller the Kb. Not surprising. Well, if we look at things like F minus plus H2O becomes HF plus OH minus, Kw divided by Ka, 1.00 times 10 to the minus 14, 3.5 times 10 to the minus 4, we get our 3.1 times 10 to the minus 10. So these calculations have to become automatic, and you have to go after the right conjugate acids, Ka. Now we're going to use it in a calculation. Calculation of pH for a weak base. NH3 is a weak base. It can accept a proton, and we're saying it's 0.100 m. So we write out this equation, and we're going to do our ice chart. So we know we had 0.100 m. We take away x, but the x is going to be very small, so the NH3 at equilibrium is going to be 0.100 m. This applies to NH3. H2O we're ignoring. Here we have our x and our x just like before. Now we have Kb expression. Well, we know this is x, we know this is x, so it's x squared divided by 0.100, and that will equal our Kb value, so we can rearrange and solve for x. But when we solve for x, we're going to get OH minus. We won't get our H3O plus directly. So we start off by getting the Kb for ammonia. And so this 5.6 times 10 to the minus 10 came from the Ka for ammonium, NH4 plus. And we get 1.8 times 10 to the minus 5. So that Ka value goes there. Have an x here, and a 0.100. We now have all our info. So Kb is x squared over 0.1 equals that. So x squared is going to equal the Kb times 0.1. So it's 1.8 times 10 minus 6. And we take the square root. And I should put a little m in here, a big M in there. Now, once I have OH minus, I can get my POH by minus logging it, 2.87. And they get my pH, I'm going to go 14 minus that value. And I get 14.00 minus 2.87. is 11.13. So finding the pH of a base, I have the extra step of calculating the Kb and the extra step of converting OH minus to POH to pH. 11.13, we get our basic pH. Our number is making sense. You may want to watch this video more than once, painful as it may be, because there's a lot of details going on.